Welcome to Area and Perimeter Part 2. Okay. So finding the distance of a line segment. It says we're not going to be given the measurements like we were in the last part. So back here when we were finding area and perimeter, it was kind of easy in some ways because we were given the lengths. Here we will not be given the lengths, so we're going to have to use our coordinate plane to figure them out. So really we are given the lengths. It's just we have to find them. Right, so whenever the segments are horizontal or vertical, finding your distance is pretty easy. You can count them, but be careful. Don't count them if they don't go up by a scale of 1. Or if you are counting them and they don't go up by a scale of 1, make sure you take the scale into account. Okay, so if each of these was worth 10, for instance, let's just pretend these are all 10 instead of 1s. The length from A to B is not going to be that how many boxes we have. It's not going to be 1, 2, 3, 4, 5, 6, 7, right? It would be 70. So, and we'll talk about that when we are calculating area and perimeter. And actually, I never count if my scale's not 1. If my scale's not 1, I'm going to use another method to find it, just so I don't make a mistake. But if your scale's just 1, right, your distance of a horizontal line, you could just count. You could also use absolute value. And that's what I would do if my scale's not 1. If my scale's 1, I'm okay counting. But if it's not 1, I'm probably going to use absolute value. And when it's not horizontal or vertical, we're going to use a third method, and that's the distance formula. And we're going to talk about that on the next slide. Now we can use the distance formula for horizontal and vertical lines. It's just we don't have to. So if your scale is 1, you have 3 different methods, and they're all fine. If your scale is not 1 for a horizontal or vertical line, I would use either absolute value or distance formula. For absolute value, and it's in right here, and here's the steps. You just take the absolute value of the difference between the coordinates, right? So, and when I say the coordinate that changes. So let's take a look here at AB. Notice that the y coordinate doesn't change. It's still 2. What changes is the x coordinate. So one way I can find the length if I don't want to count, or if the scale's not 1, is I can take the absolute value of the difference. So that would be -4 minus 3. Well, -4 minus 3 is -7, and the absolute value is 7. Let's do the same thing with CD. Right? So CD here is a vertical line. Notice that it's the x coordinate doesn't change, so I'm just going to take the difference in the y values. So the absolute value of -1 minus a -4 would be -1 plus 4. Right? So that's going to be 3, and the absolute value was 3. Now you might wonder, why did I take the absolute value? Why couldn't I just subtract? The reason is that distance is always positive. There's no such thing as negative distance. Right? Whether I walk 7 feet to the right or 7 feet to the left, I've still walked 7 feet. Right? So there's no such thing as negative distance. The absolute value makes sure that our answer is going to be positive. Right? For a distance of a diagonal line here, we have only one way, and that's the distance formula. Right? So if it's vertical, horizontal, and your scale is 1, you can count, you can use absolute value, or you can use the distance formula. If your scale is not 1, use absolute value or the distance formula. And if it's a diagonal line, we're going to use the distance formula. Right? I have some of the distance formula in your notes. And I think I included this, but I don't have the notes in front of me. I still have to print them. So if I don't have this and this and this, add that to your notes. I think I included this whole slide. But if I'm wrong, I'm sorry. Maybe I'll fix your notes. I don't know. Since I've already finished them, I don't know if I'm going to fix them. But if I didn't include that, add this part. You can just pause the tape and add this part. Now let's continue by finding the distance formula. I know this part is in your notes because I made sure to write that down, that I put this in your notes. So that I was going through the slides, I'd say, hey, write this in your notes, right? So the distance formula, we're finding the distance between x1, y1 and x2, y2. So you have 2 points. You have to find the distance between 2 points. So to find the distance between any 2 points, all you need to know are the coordinates of the endpoints of the segments. All I need to know is what 2 points do you want me to find the distance between. It does not matter which point you start with. Just be consistent for both x and y. So it doesn't matter who I say is point 1 and who I say is point 2 here. I just arbitrarily said x1, y1 was going to be 3, -2, and x2, y2 is going to be -2, 4. But it doesn't matter. Like the slope formula, it doesn't matter who you start with. Just be consistent. So to find the distance, we're taking the square root of the difference between the x coordinates, 3 minus a -2. Oh, actually, I may as well label it the same way as I have it over there. So this is x1, y1. This is x2, y2. So in other words, this would be, if I'm going to keep to what I have over there, this would be -2 minus 3 squared plus 4 minus a -2 squared. Okay. So you might think, well, why are we squaring and taking the square root? Well, the squaring is another way to get rid of the negative. When we square something, it's always positive. But then we have a value that's bigger than what we started with. That's not really the distance. So since we squared, we have to undo the square by taking the square root. Okay? And that will give us the distance. We can't use absolute value and subtract. We can't just count when it's not vertical and not horizontal. We will have to use the distance formula. And it's super simple, right? So I plugged in my values. -2 minus 3 is -5 squared. 4 minus a -2 would be same as 4 plus 2. And that's 6 squared. It doesn't really matter if I put the parentheses there because I have a positive number. It matters on the -5 because I do have to square that negative. Right, so -5 squared is 25. 6 squared is 36. And 25 plus 36 is going to give us the square root of 61. Now, in this case, we cannot simplify this number. 61 is not a perfect square. It doesn't have any factors that are perfect squares. As a matter of fact, it's a prime number. But sometimes we're going to be able to simplify it. Right? So let's take a look at what do we do if we have something we need to simplify. Okay? If it's not something we need to simplify, it's super easy. If we have to simplify it, it's just a teeny bit harder, but it's not really that difficult. So let's take a look at simplifying radicals. Right? So simplifying imperfect squares. I'm going to show you 2 ways. I'm always going to use the second way, right? Because I think it will be easier. Right? So we say that a square root radical is simplified when the radicand has no square factors. So 61 had no square factors because 61 is 1 times 61. Prime number. 33 is another one. Square root of 33 has no square factors either. Its factors are 3 and 11, neither of which is a square number. Therefore, the square root of 33 is simplified, or as we say, in its simplest form. The square root of 18, however, is not in its simplest form because it does have a perfect square. That perfect square is 9. Right? So therefore, the square root of 18 is not in its simplest form. So to put a radical in its simplest form, we make use of this theorem. Okay? And that theorem is the product property of radicals. In other words, I can take a radical and divide it up into its factors. So the square root of 18 here is the same as the square root of 9 times the square root of 2, which is the same as the square root of 9 times the square root of 2, and the square root of 9 is a perfect square. Square root of 9 is 3. Right? Because 9 is 3 times 3. Right? It's got a buddy. The 3 can come out because 1 3 goes away. When we're taking a square root of a number, we're saying, what's the number I have to multiply by itself to get 9? The number I have to multiply by itself to get 9 is 3. Can't do anything with the square root of 2. It's a prime number, and it doesn't have any factors, therefore, that are perfect squares. So simplified, the square root of 18 is the same as 3 square roots of 2. So we're making use of this product property of radicals, which says that the square root of a product is equal to the product of the square roots of each factor. In other words, I can break down a number into its factors and divide that into 2 radicals. And I can take the square root of the one that is a perfect square. So an imperfect square has a square root that's not an integer. Imperfect squares have roots that are irrational numbers. They're non-repeating, non-terminating decimals. So we are not going to change the square root of 18 to a decimal number. What we are going to do is simplify. We're going to factor out the perfect square. So when we simplify radicals of numbers that are not perfect squares, we're going to take the roots of all factors that are perfect squares. Okay? And I'm going to do one example, and then I'm going to do more examples in class on, I think on class on Tuesday. I don't know. I had told myself where I was going to get by the end of Monday. And so let me see how long this takes me. This is the one I have in your notes, 5,880. I'm going to use what's called the buddy method. It's essentially the same thing as I did over here, where I broke it down into its factors, and I took the square root of 1 and then of the one that was a perfect square. But I think the buddy method is a simpler way to write it down, and I think you'll find it easier to work with. All right. So I say there's two different ways. You can figure out what's the largest perfect square and take the square root of that. Or you can use the buddy method and just break it down to prime factors, and you're looking for pairs of like factors. This one tends to be easier because sometimes we don't know what the greatest perfect square is. And so long as you follow these steps, you won't make any mistakes. Okay? So we're going to divide. We're going to take, so we have the square root of 5,880 here. This one's in your notes. I'm just going to take it out of the radical because I'm figuring out its factors. Right? And then I'll simplify. When I simplify it, we'll make sure it's under the radical. All right, so you divide it by any factor at all. Doesn't matter. You might look at this and say, I don't know what it's divisible by, but I see it ends in a 0, so it must be divisible by 10. And it is. All right, so 5,880 divided by 10 is 588. Neither of these is prime numbers. So you're going to keep dividing until you have only prime numbers. So 10, 2 divides evenly into 10. 10 divided by 2 is 5. 2 and 5 are prime numbers. They're only divisible by themselves in 1. 588 is not prime because it's an even number. Okay? So we can divide by 2. Right? 588 divided by 2, let's see, 2 goes into 5 2 times. I have 1 left over. So 2 goes into 18 9 times, and 2 goes into 8 4 times. Right? 294, not prime. Right? I don't want to run out of space. I wonder if it's divisible by 4. No, not divisible by 4. So 2. All right, so 2 divides evenly into 294. 2 goes into 2 1 time. 2 goes into 9 4 times with 1 left over. 2 goes into 14 7 times. Now 147, is that prime? Well, no, because I can figure out a number that divides evenly into 147. I hope you recognize it. 14 and 7, it's got to be divisible by 7. If you're not sure, you have a calculator. Keep trying, right? So it's got to be divisible by 7. Right? So 7 goes into 14 2 times, and 7 goes into 7 1 time. 21 is not prime, and we know those factors. 21 is 7 times 3. Let's just move everybody up just ever so slightly so I can squeeze in the last 2. And by the way, the order that I chose to divide in does not matter. So I could have divided by 2 the whole time until I ran out of 2's. Or I could have said, okay, 5 plus 8 is 13, and 13 plus 8 is 21. 21 is divisible by 3, therefore 5,880 is divisible by 3. Does not matter what number you start with, so long as you take it down to its prime numbers. Now I have nothing but prime numbers. We're going to find matching pairs of numbers. The only values we're dealing with are the ones at the ends, because everything else has been broken down. Just the ones at the ends. All right, so when I find my matching pairs, I circle one and cross off the other. Right? My factors here are in radical prison. Right? The radicand there, the radical sign is a prison, and you need a buddy to get them out. Right? So 1, 2 here needs his buddy, the other 2, to get him out. Unfortunately, his other buddy is killed trying to get him out. All right? 5 has no buddy, he stays in the prison. 2, I don't have another 2, it stays in the prison. 7 has a buddy that's going to get him out of radical prison, and he's gone when he gets him out of radical prison. There's a 3, I have no other 3s. So the numbers I circled come out of the radical. I think so, right? And right down here I have all the steps. So I'm up to step 4. The circled factors come out of the radical sign. We already found the matching pairs. We circled 1, we crossed out its buddy. Circled 1s come out, so 2 and 7 come out. And we broke it down to its factors. When you break something down into its factors, you're dividing. To put it back together again, I have to multiply. So we're going to multiply 2 times 7 coming out of the radical. And anybody who is not crossed off and not circled is going to stay in the radical. I've got a 5, I've got a 2, and I've got a 3 that's going to stay in the radical. So this is going to be equal to 14 times 5 times 2 is 10 times 3 is 30. Right? And 30 is as simple as it gets because it has no factors that are perfect squares. Its factors were 5, 2, and 3, and none of them are perfect squares. And now we've simplified our radical. Right? So you're going to drop the crossed out buddy factors and multiply. The ones that come out get multiplied. The leftover factors stay in the radical and they get multiplied as well. Okay? And that's how you use the buddy method to simplify your radicals. And this is the method we'll use to simplify radicals. So the one other page I wanted to finish was this page here, where we practice simplifying some radicals. And we practice finding the distance a couple times. And then I had a whiteboard practice. And then I was going to start the next lesson on Tuesday. So we'll have to finish up those last couple slides, and then we'll start with perimeter on the coordinate plane on Tuesday. Bye for now.